Welcome back. In this video, I wanted to just cover some more gradient examples, work some that are a little bit more complicated, and then also show how the gradients works in higher than 3 dimensions when you've got like, 4 or more input variables or something like that. So let's just go ahead and jump in with some examples. Our first one is going to be f of xy is equal to x squared y to the 5th. And if we remember our definition of the gradient, what we are looking for is a vector that has the partial with respect to x in the x component and the partial with respect to y in the y component. So the partial with respect to x of this vector, or this function here is 2x and then y to the 5th. And the partial with respect to y is going to be 5x squared y to the 4th. And this one's pretty simple. That's all there really is to taking those two partial derivatives. So our gradient is just going to be this vector right here. Let's do another. We're going to look at g of xy is equal to x squared sine x plus y to the 4th. Okay, so once again, our gradient of gxy is equal to the vector that contains the partial with respect to x in the first component and the partial with respect to y in the second component. So our partial with respect to x, we have an x squared times sine of x plus y to the 4th. So since we have these two functions of x that are multiplied together, to get this partial derivative, we're going to have to apply our product rule. So the product rule says that we'll take the derivative of this piece first, leaving this piece alone, and then we will swap. So derivative of x squared is 2x, and then we leave the sine x plus y to the 4th alone, and then we add to it the x squared left alone times the derivative of sine of x plus y to the 4th. And this is just going to be cosine of x plus y to the 4th. Normally, we would just apply the chain rule, and I mean, I guess we have applied the chain rule here. If you take the derivative of the inside of this guy here, you're just left with a 1 because the y to the 4th would drop off, and then the x becomes a 1. So that's really all there is to that derivative there. And then I'm going to put the second component on the next line. We need the partial with respect to y. The x squared times sine x plus y to the 4th. This is the only part that has a y in it. So the x squared just kind of stays here and gets multiplied by the derivative of sine of x plus y to the 4th. So we'll have cosine x plus y to the 4th. But chain rule says that we have to take the derivative of the inside here. So that's going to give us 4y cubed as something else that's multiplied there. So I can write this out, 2x sine x plus y to the 4th plus x squared cosine of x plus y to the 4th. And then my second component on the second line is going to be x squared. And I guess I'm going to put the 4 out here because convention says that you would typically just pull the 4 out to the front. Y cubed cosine of x plus y to the 4th. And that's pretty much all there is to that. For my next example, I wanted to take a little bit more complicated partial derivative. So we're going to look at the function h of xy equal to 2x plus 2y divided by the square root of x squared plus y squared. Okay. So gradient of xy is partial with respect to x in the first component, partial with respect to y in the second component. So I'm going to have to take this derivative. I'm going to rewrite it. So I'm going to put the square root in an exponential format. So we have x squared plus y squared raised to the 1/2 instead down there on the bottom. Okay, so I'm going to take the partial with respect to x. And since there is an x in both the top and in the bottom, we're going to have to apply our quotient rule, which says that we take the bottom, so x squared plus y squared to the 1/2, times the derivative of the top, which is just going to be 2, and then minus the top, times the derivative of the bottom. And here we're going to have to apply the chain rule. I'm going to have 1/2 x squared plus y squared. And then that's raised to the negative 1/2. And then this will be multiplied by the derivative of the inside here. So that's going to be times 2x. All of this is divided by the bottom part squared, which just gives me x squared plus y squared, since squaring that denominator is going to cancel out the exponent of 1/2. Okay. So I'm going to kind of rearrange this a little bit. And we can actually simplify this down quite a lot. So we're going to go ahead and do that. This 2 can come out here. I'll have to put that square root back. X squared plus y squared, and then minus this 2 and the 1/2 will cancel out. So I'm just going to be left with x times 2x minus 2y, and then times x squared plus y squared raised to the negative 1/2. And all of this is divided by x squared plus y squared. And there's actually one more step that we can take to simplify this down even farther, and it might not be immediately obvious, but it's a pretty common trick, is we're going to multiply top and bottom by square root of x squared plus y squared, just like so. Okay? And what's going to happen when I distribute this square root to each of these two pieces here, the square root of x squared plus y squared times the square root of x squared plus y squared is just going to leave me with x squared plus y squared. And then we're subtracting off 2x minus 2y. And then this is basically 1 over square root of x squared plus y squared, because we have that negative 1/2. So it's actually going to cancel with this guy right here. And that's just going to leave me with a 1. Okay, so this piece times this piece becomes a 1. And then we're dividing by x squared plus y squared raised to the 3/2. And this actually allows us to simplify down even farther, because I'm going to distribute the 2 here, and then this x gets distributed across. And so this 2x squared and this, what becomes a negative 2x squared, is going to cancel out. And I'm left with just 2y squared. Oops, those should be pluses. Plus minus 2xy. And then that's all divided by x squared plus y squared raised to 3/2. So this is way, way simpler than what we started with up here. So just by applying, not necessarily a super obvious simplification, but a really great trick to kind of keep in your back pocket to remember that we can use here, multiplying top and bottom by that square root of x squared plus y squared, really allowed us to simplify down quite a bit. So we can kind of end here with this partial derivative. Now, I'm going to tell you right now that the gradient with respect to y is exactly the same process, except we wind up with a slightly different answer. So I'm just going to show you what that looks like. And if you want, you can feel free to go through all these steps on your own, but just know that it's exactly the same idea. It winds up being 2x squared instead of 2y squared. We get 2x squared, but then it's still minus 2xy, and then divided by x squared plus y squared to 3/2. So this uses the exact same process as hx. Okay. So we can take this piece and this piece, which is hx, and put those into our gradient. So we're going to have 2y squared minus 2xy divided by x squared plus y squared raised to 3/2. And then 2x squared minus 2xy divided by x squared plus y squared raised to 3/2 for the second component, just like that. So a little bit messy, but it's kind of nice that since there's actually a lot of, I guess you can say, like symmetry between x and y here, the result for y winds up being really super similar and can use the exact same process. But yeah, so that's pretty much all there is to doing that kind of problem. One more example of taking a gradient. I want to show how this works if we have even more input variables. Suppose we have the function f, x, y, z, and then a fourth variable w equal to w squared, x cubed, y to the fourth, z to the fifth. Well, remember that the gradient has a component for each partial derivative, which means that in this case, our gradient is going to look like the vector that contains just each partial derivative. So fx in the x component, partial with respect to y in the y component, partial with respect to z in the z component, and then partial with respect to w in that w component. So all you do is for each extra variable, you just tack on an extra component in your vector here with the gradient to put your partial derivatives into. So exact same process, we just have more pieces. So here we take the partial with respect to x, and that's going to be 3w squared, x squared, y to the fourth, z to the fifth. Take the partial with respect to y, and we're going to have 4w squared, x to the third, y to the third, and then z to the fifth. And I guess I have to continue on to the second line. We'll take the partial with respect to z, which is going to give me 5w squared, x to the third, y to the fourth, z to the fourth, and then the partial with respect to w. So we'll have 2w, x cubed, y to the fourth, z to the fifth. So again, exact same idea. All we're doing is just tacking on extra partial derivatives there. Okay, so another common type of problem that you might look at with the gradients is just finding the gradient at a specific point. And all you got to do is, well, find the gradient and then plug in the points. So, for example, if we kind of go back to the function f of xy equals x squared y to the fifth, and we want to find its gradient at the point 3, -2. Well, we said earlier that our gradient was 2xy to the fifth and 5x squared y to the fourth. All we got to do is plug in 3, -2. So we'll have 2 times 3 times -2 to the fifth, and then 5, 3 squared, and then -2 to the fourth. So computing both of these components, you're going to wind up with the vector -192 and then 720. We can look at one more like this. Let's say g of x, y is equal to x sine of y at the point 2 pi over 6. So the gradient here, we actually did not compute this one earlier. So gradient partial with respect to x is just going to be sine of y. And the partial with respect to y is just x cosine of y. All we got to do is plug in these points. So we're going to have sine at pi over 6, and then 2 times cosine at pi over 6. So generally speaking, I strongly encourage that you have at least the first quadrant of the unit circle memorized. It helps out a lot, especially with these kinds of problems. You'd be amazed by how much easier a lot of calculus will become once you just simply have these values memorized. You can kind of start making some new connections there. Sine of pi over 6 is equal to 1/2, and then cosine of pi over 6 is actually √3 over 2. So we're going to wind up with 1/2 √3 as being the vector for the gradient at the point 2 pi over 6. But that's pretty much all there is to these kinds of problems. The gradient, all you got to do is compute that partial with respect to x, partial with respect to y, and then if you want to plug in a point to figure out what the vector is at that particular point, you just take the point and you plug it into the gradient. So that's pretty much all there is to that.